Well, welcome back. We're continuing to design and lay out our 5.8 gigahertz MMIC LNA in the TriQuint PED process. And in this segment, we're going to wrap up the layout in a sense by getting the complete layout ready to go for verification and LVS and DRC. But at the end of this segment, we'll have a fairly complete layout that we can consider as a whole. Let's begin by going back to the simulation and just refreshing your memory of where we were in terms of gain at about 18 or 19 dB a gain. In terms of noise figure, we're at about 1.7, 1.6, and we're still going to be a little concerned about stability as the design progresses, so we may want to adjust a few things here and there. Let's go over to the layout now. And you can see that I've pretty much laid things out as you might expect, going from our input here on the left to our output on the right. Here's our nice big polygon cap that we decided we'd play with earlier. I've laid that out a bit, and I've got my my first stage, my second stage, and some bias resistor here, our matching inductor here, and our resistors for providing a drain resistance for the two stages here. So this would be our 3.3 volt supply. Now what I want to show you today is a feature called iNets, and this is helping us to do the final routing, if you will, once we've got everything placed the way we really want. What iNets allows us to do, or as it has allowed us to do, as you've seen, is put off the routing of lines till the very end of the process, or to treat the lines as things that we may want to be very flexible about, but not necessarily capture in the schematic. So what I have here are some fly lines that I still haven't routed yet, and I thought I'd show you how we can use the iNet feature to finish routing off those lines. The first thing that we can do is we can set some default routing structures. So here I have my both horizontal and vertical routes being done in 10 micron wide metal 1. Let's click on this box here, and we'll also allow ourselves to have metal 2 in the vertical dimension. Actually, I want metal 2 in the horizontal dimension, as you'll see in a minute, and I'll keep that metal 1 for the vertical dimension. And what we'll do is we'll just zoom on in down here to our bias resistor. Now this resistor is providing some isolation, if you will, from a bond pad that we may want to use for some bias control. In our initial design, we were thinking about 0.5 volt here because these are enhancement mode devices, and this would put the bias on the gate of those devices. Additionally, we may want to go back and redesign this so we can, off the 3.3 volt supply, just step down to 0.5 volt and provide that directly to our circuitry, but have an alternative here that we could go ahead and provide an external bias or bias control if the process shifts a little bit, or if we have some sensitivity to input or output match we didn't anticipate. So let's go ahead and route this resistor to our bond pad. And I'll start off by double clicking the line, and you can see that I have a routing tool that gets highlighted, as well as the begin and end point of my route. So I'll just start over here at the resistor, and I'll click once, and you see I have my metal 1 coming down because that's the default vertical route. And if I click over, it changes to metal 2, and then we'll get centered there and click over again and finish up. I'll double click a little short, and we can use our snap to fit function to finish off that route for us. Now, if we look real closely, you can see that there's vias that have been inserted for us. We'll go ahead and bring up the 3D view and zoom in on that. But you can see that we have a 10 micron wide line on metal 1 coming into a 10 micron wide line on metal 2, and then back to metal 1 again. And if you look real close, we have our vias automatically inserted for us. So that's what iNets allows us to do, is very quickly, very easily route our lines in a fashion that's fairly intuitive and gets the job done rather quickly. Let me show you another feature of iNets where we can make automatic T-junctions on the fly. Now here I'm going to go back and let's just do things in metal 1 for a change, and we'll see how that looks. I can also change layers on the fly by going in and selecting the properties of these lines once they're routed. I'll start off by routing this line here. We'll just go up. And I like finishing off with the snap to fit tool, so I know that I get the proper line length right up abutting to the pin location of each of the devices. Now over here I'll do the same thing, but instead of routing over to the pad, we'll jog down here, and come on over into that line segment. Okay, and you can see that it's formed a nice little junction there, and it's by doing that, it's told us that it's made the connection properly. And if we look in over on the 3D, you can see we have a nice route. And that's all there is to iNets. It's rather simple and gets the job done very effectively, but we've been able to put off the realization of those nets till very much later in the design process because we don't anticipate that they're going to affect our performance all that much. Now to take a look at that in point of fact and to figure out what that impact would be, we want to go back to the schematic and use another really great feature. This is one of my favorite features in the AWR design environment because it really leverages the concurrent data model and the richness of all the tools that you could bring to bear on a problem such as a MMIC design. So you can see here I've got an extract block that I've put down on the circuit, but it's disabled for right now. What that means is that all the elements and wires, if you will, are going to be captured in their intended modeled state. So for a microstrip line, we're going to use the MLIN model. For a resistor, we're going to use the value of the resistor, the resistance model that's built into the kit. But for these wires that we've routed as an iNet, we're just going to ignore them for the time being, which is essentially what we've been doing. So if we go to our simulation and get our baseline simulation there, I'll freeze that for a minute with the Control F, and we'll go back to the schematic, and now we'll enable that that block, and we can go ahead and simulate that now and look at the impact of extracting this. And I'll just talk about what I'm using to extract here in a second, because you'll see that I have some rather different messages that have come up in the simulation box. We'll put that aside for a minute and look at our simulation results. Now you can see that essentially they're the same as the simulation results before we did the extraction, but a couple of things have happened. You can see that down here at the low end, or actually at the high end, we've shifted a little bit over. We have a bit more gain than we did before, but sort of more importantly, we've picked up some extra stability. We have some extra margin now where we didn't have before, simply by including those interconnects in our analysis, because there is extra loss associated with them, and that does impact the design to some degree, as well as there's additional couplings now that are captured in the design. So how did we incorporate those couplings and those extra losses? Because the simulation was rather fast, and Axiom is incredibly fast, but this maybe was a bit more quickly simulated than you would have anticipated, especially as I've been telling you about my slow laptop here throughout the video series. We actually used a circuit extractor, not an EM analysis engine. We used ACE, and what ACE does is it takes the very same extraction, the very same artwork, and puts it in an EM document, but instead of analyzing it with Maxwell's equations, ACE attempts to match each bit of line length to a microstrip or strip line or other distributed model that it already knows about. So it's able to look at microstrip line lengths with loss. It's also able to look at couplings. And if you look at our simulation results, you can see that one of the things that it was doing was executing an EM quasi-static model. So inside of ACE, we're actually using very highly optimized EM analysis to focus just on those bits of the problem that require EM analysis and leave the bits that are just isolated microstrip line to be modeled in that way. So here we've actually captured some couplings using highly optimized EM solvers, so we get that additional bit of accuracy. And that's what's been able to contribute to our improved gain, if you will, as well as giving us a bit more stability margin than we initially had. Well, there's nothing stopping you from switching this over and doing Axiom or any other of the EM solvers plugged into the EM socket, but I promised you that we'd get to the end of the layout bit here, or at least get to a completed layout. So let me do that before this video segment ends. And fittingly enough, I call it completed layout. And we'll go ahead and let me just get it down to where we can look at the two layouts together so you can see the differences that I've introduced in my final layout, if you will, or the layout that I think is going to be my final layout, because things change as we go through verification. So I'll tile these. Let's tile them horizontally so you can see sort of the difference between the two. Now, one of the major differences is that this final layout, or complete layout, if you will, is a bit more compact. It probably could benefit from even more compaction, but the design is smaller in both the X and Y dimensions. Additionally, you will have noticed that I would have gotten rid of that really ugly route that went around that bond pad. I'll have two VDD pads now, and one for the second stage and one for the first stage, which probably isn't such a bad thing. It gives us a bit more isolation between the two. One of the things we'll have to look at when we after we fabricate this chip is we'll have to look at some packaging effects, because there will be separate bond wires over there, and that may add some complexity to our consideration for stability. But in general, the design is roughly the same. It's a bit smaller. I've pulled in the line links here on the input that previously we saw weren't a big factor. And effectively, this is the same design, although compacted a bit. And as I mentioned, it could suffer, if you will, from a bit more compaction. But before we leave this segment, let's go ahead and take a look at the performance that this gives us, and we'll be able to compare the last layout to this one. And you can see here again that compared to our previous layout, we have a bit more stability and a bit more gain, and noise figure is still looking really good. So that's our TriQuint LNA MMIC design in a nutshell. We've gone from considering what is noise figure and cascaded noise figure and how we may want to architect our LNA. We've included aspects of a detailed study of the FET and where we should bias it. We've looked at noise circles and stability and maximum gain and minimum noise figure. And we've sort of developed this approach of incrementally adding complexity along each step of the way, gaining a deeper and deeper understanding as we get closer and closer to a real design. Having started with a very ideal design, we've taken an approach which allows us to pinpoint at each step of the process the decisions that we've made based on insight that we've had into the design as we've gone from conceptual design to an actual schematic to an implemented layout. Well, that's pretty much designing a MMIC LNA in a nutshell. We may in the future come back to this design and look at things like verification, look at LVS and DRC, look at packaging, and perhaps look at a more compacted layout. I hope you've enjoyed this. I hope you've learned something from it. If what I've done looks exciting, I would encourage you to go and download a copy of Microwave Office and try this out for yourself with the AWR MMIC process. If any of the features along the way look interesting, there's plenty of information in the documentation, in the Getting Started guide, lots of AWR TV videos, white papers, application notes, and of course, if you have any questions, please contact AWR or AWR Sales Professional.